might be objects that you want to transport or sensors that you might want to use to map the environment. And cooperation is a fundamental aspect of all of this. And here we've been working with biologists, and this is a video shot by my collaborator Stephen Pratt at Arizona State. Nature offers several examples where groups accomplish tasks that individuals cannot accomplish. So what you see here is a piece of fig that the ants are transporting back to the nest. And if you look at this video, it's quite clear that there's no central ant who's calling the shots, right? The ants do signal each other, they're close to each other, but no ant actually knows how many ants are part of this group. All the coordination is very local. And these examples are not limited just to ants. There are certainly other examples. For example, here you see photographs of 1 million starlings flying in from all over Europe, assembling in Denmark to form these incredible formations. And again, there are three things that I'll submit to you that are similar to ants, these birds, and to our robots if we have to make them cooperate. First, they operate just based on local information. It is not possible. There are 4,500 people here. I guarantee you that the person at this extreme doesn't know what the person at the other extreme is doing. So you have to act based on local information. Secondly, you have to act independently. There's no one who's going to tell you exactly what to do in order to accomplish this cooperative task. And then finally, there's got to be this notion of anonymity. What I mean by that is an individual has to be agnostic to who her neighbor is. That's very important if you want to perform a collaborative task. So the ants have no identities. The robots don't care which robot is next to each other. So I want to show you a video that we've just created. This was about 6 months ago, which shows the biggest indoor swarm that we've managed to create. So these are these really small robots that I told you about. There are 20 of these flying in formation. They're all aware of their neighbors. They all solve this problem going from A to B. But they're told by the human operator to create these formations. And these robots create these formations in a safe way, keeping track of their neighbors. These formations can be 2-dimensional, 3-dimensional. They can change dynamically to go through obstacles. And again, the control has to be very, very precise, as you see in this video, where they traverse a figure-8 pattern. And these robots come within inches of each other, and you can imagine the level of precision that's required because they're buffeted by the aerodynamics of their neighboring vehicles because of the downwash from the rotors. So this is an example where the robots are just creating formations. It makes for a cool video, but what we'd really like to do is to get them to collaborate to carry objects. And so here you see teams of 4 robots carrying payloads that individuals simply could not have carried. Now here there's a disadvantage. You can see if you group many robots together and have them carry one big payload, the overall inertia of the system actually increases and the maneuverability decreases. But what you gain here is, again, the ability to carry larger payloads. And so here you see these robots actually collaborating on identifying a piece of 2x4 and then figuring out how to grasp it. And these are grippers made out of composites with inlaid fish hooks, which allow you to sort of dig into these 2x4s, pick it up, and they're able to move. The next example I want to show you is an example of construction. So here there are 3 robots that are assembling structures based on blueprints that look roughly like what you see in a Lego instruction booklet. So the robots are told what the pattern needs to look like, a 3-dimensional structure. The robots decide which robot is going to pick up what part and assemble it where. And here you see, fast forward, 3 experiments where the robots essentially build 3 different 3-dimensional structures. Again, the high-level specification is very simple, but the robots make all these decisions on their own in order to satisfy that high-level specification. So in all these videos, one of the things you would have noticed is this network of motion capture cameras. This makes for a very, very special piece of infrastructure, and if these robots have to leave the laboratory and go outside, it's hard to do. And so we've been working on figuring out how to get rid of that infrastructure, how to eliminate the need for that infrastructure, and here's our first attempt to do that. So this robot has two pieces of hardware. One is a laser scanner that essentially produces a 2D cloud of points at a 270-degree field of view out to about 30 meters. The second is an off-the-shelf Microsoft Kinect RGB depth camera that is again good to between 3 meters to 5 meters out with a 40 degrees field of view. Using both these sensors, the robot can now start distinguishing features in the environment and triangulating of those features. This allows the robot to localize. As I'll show you in this video, where the robot essentially takes off outside a building it's never seen before. It builds this map that you see on the left-hand side, which essentially is a collection of all the features that it sees. And then it's triangulating its position with respect to these features 100 times a second. So those motion capture cameras are gone, but the onboard cameras provide roughly the same information. And the reason I say roughly the same information is because these robots like this, don't have any access to a global coordinate system like GPS or our motion capture camera system. What they have to do is to triangulate with respect to features that they have located, and so they have a relative sense of how fast they're moving. But as you can see here, this robot is completely autonomous. The student who is operating this can only see the video that you see on the left, the map that you see on the left. And based on that, he can essentially command the robot to go inside a building and look for whatever information that might be relevant to the particular mission. And again, you see the camera pictures coming that the robot sees on the top right. That gives you a sense of what is actually visible to the robot, but that information is never relayed back to the human operator. The human operator only sees the robot's internal representation, which is on the bottom left. So we've used robots like this, as I told you, shortly after the earthquake. We went to Fukushima and Sendai, and this is an early experiment we did in one of the collapsed buildings. So this is in collaboration with our collaborators at Tohoku University. They created this ground robot, and the reason our robot is hitching a ride is because it's programmed to be lazy, just like humans. And the reason for that is simple. It's about the limitations of the batteries that we carry. So because we want to extend the mission life, the robot hitches a ride whenever it can. But here you can see it's confronted by this obstacle. The ground robot cannot proceed any further. It releases our aerial robot. The aerial robot goes in over this bookshelf, which is actually impossible for a human to actually go across, through this buckled doorway, and it's able to recover this three-dimensional information. And it integrates this three-dimensional information with information that the ground robot has, allowing this air-ground collaboration between two very different types of robots. And to just give you a quick idea of a mapping experiment we did, so this is the 7th, 8th, and what remains of the 9th floor of a building in Tohoku University in Sendai. This was again done 3 months after the earthquake. And you can see that the robots have collected all this information and integrated it into a map. Now this map may not be easy for you or I to visualize, but remember that if you wanted more information, you could actually get it from the robots that have access to even more information that you see over here. So one other thing I really wanted to talk about is the ability to bring together aerial robots technology along with music and lights that really lends itself to new art forms. So this is not my work, this is not our lab's work, but my former students who have now established a company, came out Robotics, did this performance at a Saatchi & Saatchi marketing event. So what you see here is 16 of their robots coordinated with laser lights with 16 different actuators, all synchronized perfectly and choreographed to music. So art forms like this are now being enabled by a really cool mix of technology and music. And I think we'll see a lot more of this in the years to come. But next, what I really want to do is to show you the coolest video I have. And it behooves us to show it here, the coolest conference I've been to in my 50 years. This is the James Bond theme song, celebrating 50 years of James Bond. And let's watch 9 quad rotors, playing the theme song, and I'm going to shut up and let you listen.